Good morning, class. It's not going to be the same this semester without being able to see you, but here we go. I hope you're all well. I still have a bit of a lingering cough from the cold I had, so please excuse any coughing. Like that. All right, this is the introduction to the current problem sets 14 and 15. So let's get into it. All right, problem one here. So we know the virtual address is 32 bits from this. I'll let you convert this to the page number field size in bits. You know, any bits here for the physical address. Here's a 32-bit virtual address. So explaining how the system maps from a virtual address to a physical address should be fairly straightforward. All right, question two. You're going to write an algebraic expression given a particular page fault rate. Let's say 1%. 1% of the time we have a page fault. 70% of that 1%, the page is modified. So it needs to be written out to disk. The other 30% of the 1%, it's not modified. And under that condition, the page does not have to be written back to disk, right? Because it hasn't changed. 99% of the time, there's no page fault. So 99% of the time, the memory access, the effective access time is 100 nanoseconds. Okay, so you're going to write an algebraic, you're going to put that in an algebraic expression with the effective access time on the left-hand side. Plug in 200 nanoseconds for that, and then solve it for what the acceptable page fault rate is going to be. And it's going to be much less than 1%. Keep in mind a millisecond is 10 to the minus 3 seconds. A nanosecond is 10 to the minus 9 seconds. Okay, in this problem, we have a process that's accessing these pages. It has 3 frames to work with. They're initially all empty. And you're asked to compute the page fault rate for each of these 3 algorithms. There's a brief example. Let's say we had a random page replacement algorithm. We hit 7. Remember, the frames are empty. So this is a page fault. We hit 2, another page fault. 3, another page fault. Now the frames are full. 1 results in a page fault, and we have to select the victim page. Let's say that 7 is selected as the victim page. So 1 replaces 7. And then with 2, since 2 is still in a frame, there's no page fault. On the other hand, if when we were selecting the victim page to be replaced by page 1, if we had selected 2, then this access to page 2 again would result in a page fault because page 2 is no longer in memory. Okay, let's move on to problem set 15. Okay. This one's kind of straightforward once you realize what's going on. Given this system utilization, or the CPU's not being utilized, it has a lot of idle cycles. And the paging disk is heavily utilized. It kind of looks like the system's thrashing to me. So keep that in mind as you consider whether making each of these changes individually improves CPU utilization or makes it worse. Okay, let's see. 2, I think, should be fairly straightforward. 3, keep in mind that the objects in this lab are being allocated and deallocated quite frequently. And each cache is a shared resource. Keep that in mind and think of the CPUs as being separate processes. Right? We have this is a thing of this is a multi-core system, and each processor's running different an individual process. Right. So if it's an 8-core system, if it's an 8-core system, for example, we have 8 processes running simultaneously. Right. So keep those things in mind as you think about question 3. All right. There's the introduction. We can use the discussion on Canvas to ask questions, and I'll either reply there or do a follow-up video if that's necessary. All right, you guys all take care. See you soon.